All right, guys and girls, today we're going to discuss graphs of derivatives. So what I'm going to do is we're going to look at a picture of a graph and figure out his derivative. Now, graphically, we've looked at how we can find this as a function and as a value, but as in terms of a graph, it represents the slope of the original function. That goes back to the whole instantaneous rate. That's the slope at a point. So the slope values of the functions that we're looking at, the pictures we're going to look at, you got to think of the slopes of the graph are going to be the y values of the graph of the derivative. So what I have here is I've got 4 examples that we're going to look at here. We're going to discuss their slopes and try to figure out what the graph of the derivative would look like for each one. So I'm going to go through this slow process. It's slow because that's just how the speed I'm going to move. These problems really, once you get the hang of it, shouldn't take you all that long. It's not that big of a process. Let's look at the first graph here, which I have A. And by the way, down below, I've got some pictures of some matching, but I want to go through the longer process of actually drawing it because for tonight, that's what you're going to have to do. So you're going to have 9 graphs that you need to look at like this and figure out how does the derivative look each time? What's the slope doing each time? So notice below, I've got some blank coordinate axis, and I'm just going to kind of draw my best what the heck's going on. So I start at the beginning of the graph here in the far left, and it's up here. That's nice. But what's the slope doing? Well, you may argue that the slope is negative. And you're like, yeah, you're right. Slope is negative. Not only is it negative, but it's very negative. So what I'm going to do is next to the graph, this is just how I do it, is I draw a relatively large negative sign to show that graph, the slope is very negative. I don't know what the number is in terms of what the slope value is, but I just know that it's pretty darn negative. Now, because this is a nice smooth curve, not any jagged lines or doing anything crazy, it still remains negative up to this point here. Now, at this point here, we've got, all of a sudden the slope actually becomes a horizontal tangent. The slope there is 0. So let's think about numbers. Nice smooth curve, so not a lot of changes going on. Starts very negative and goes to 0. So that means that number is going to remain negative, just not as negative. So I make my little negative signs a little bit smaller. They start out pretty big and they get a little smaller. Kind of describe what's going on. So you would say that value could be increasing, starting off negative and getting increasing. And then for a while, our values get positive, and then by the time they reach up here, they end up getting back to 0 again because we have this, what we call relative maximum, which has a horizontal tangent there. So think about that. Where 0, we're, in terms of positive numbers, we're small. My positive values start increasing, and then they start going back down. Then after that, we've got negative values, and it starts off not as negative, but you could see by the end it gets more and more negative. Again, address the slope. That's how I got those pluses and minuses and zeros. All right, so now down below, I'm going to try and do my best to draw what the heck's going on. The easiest thing to do is to spot out the zeros. Take those zeros, the relative min, the relative max. Bang and bang. I'm just trying my best to line it up. I don't know how successful I was. So that means the derivatives are going to cross the x-axis there and there. Now let's think about this. Very negative approaching that 0. So you could say very negative approaching that 0. Gets positive for a while, hits some sort of maximum on that positive value, and then comes back down. How about that? Then it starts taking off, becoming more negative. So this top guy right here would be the f, and this guy right down below would be the f prime, the graph of the slopes. Another observation to make is this value where it becomes most positive. Earlier in the year, we discussed that point. It's called the point of inflection. That's where the slope either maximizes itself or minimizes. So where that concavity changes should make a maximum or a minimum on your derivative graph. Keep that in mind. All right, let's look at the next example here, B. In the image of B is a series of straight lines. Now, the thing I know about straight lines is the slope is constant all the time on those little straight segments. So yeah, you could tell me that this slope is positive. Bam, bam, bam. And it's not changing. It's positive, not changing. Then we hit a point. Now it's a point. Now literally, it's like pointy, not a smooth curve like the last one. When you have a graph, a function f, where he's pointy like that, there's no slope at that point. It's what we call a point of non-differentiability. We'll talk more about that in our future. But just for today's purposes, there's no derivative at the points. There's no values there. No there. And there too. You could say that as well with that other point. So pointy graphs, just know that they're going to have no slopes there. We'll discuss how that looks on the graph in a minute. All right, so this little segment here, it's negative, and it's just constant negative because it's a line. So these negative parts, and then afterwards, after that other point, again, back to positive. You could argue that by looking at these slopes are the same on the two positive pieces. So it's okay with that. So let's think about that. We've got a positive value that's not changing. So as far as the derivative goes, looks like a horizontal line, right? Now that spot where there's no derivative, we're going to put a hollow circle there. We can do the same thing with this other value over here. I'm just jumping ahead there a little bit, and then it's positive again. And I put those lines pretty much at the same height because I estimated that these slopes were about the same. Now the middle section where it's negative, so I got to go down below the x-axis, and again surround him with hollow dots because there's no values of derivatives at those spots, and make the value horizontal because that slope's not changing. It's a nice line, so it means the slope is consistent, and it's negative. Again, the y values in the second graph are the slope values of the first. Keep that in mind. Okay, let's scooch ahead, see how this other guy looks. All right, now starting off here, ooh, not much of a slope at all. Pretty close to zero. Pretty close to zero because he's kind of flat. You know, he's almost like a maximum or minimum. I can't call it a maximum or a minimum, though, because I don't know what's happening to the left here. Like all of a sudden, does it turn up or something like that? Or does it wrap down? Because if it wrapped down, then it'd be, but I don't know. I can't assume things. You know what happens there. All right, so we have this value. Let's say it's pretty close to zero. And what happens is it looks like it's very negative. Not very negative, very slightly negative. And then it gets a little bit more negative all of a sudden, and then it goes back to zero, kind of like it peters out. So we have a brief moment in time where it's going to sound weird, hit our most negativeness. I know, that's not really words. After that, we start becoming, we get pretty damn positive. And then look at the slopes. They start to kind of peter out, so they're not as positive. All right, let's try to turn that into the graph here. So we got the zero, looks like it's lining up out there, that maximum is going right there. So we have some negative values, and they get pretty negative, but then they get back. So they start pretty close to zero, they get something like this, and then they come back to zero, something like that. Negative values. Not very much, not very far down from the x-axis because those values never got really big in terms of their slope values. All right, positive values. And then it gets back, then it starts coming back down like that. Well, in second thought, I'm gonna change how this looks a little bit. I just had a little bit of an epiphany, right? Because it gets its most negative right before it goes back to zero. So something that looks like that, I'm gonna go with. Right? This might describe the slopes of these. All right, let's look at the last one. Now let's start putting all of our facts together. Kind of jump ahead. Facts like relative maximums and relative minimums become zeros on the derivative. This is a very positive number, and he's getting towards that zero. And it's this nice smooth curve again, so it's very positive. Then we go negative for a little bit, and then we pop back to positive. So it looks like somewhere around here we got that point of inflection. And you could say the same thing over there, where it starts making positive, hits its most positiveness, and then back down to zero again. And then we take off to Never Never Land. All right, so let's see if I can put this all together. Ooh, that's looking pretty good there, turn chalk. All right, so it started off very positive. All right, the slopes were very positive, and they went down to zero. So there they are. Notice I tried to line up the x values as good as I could, to model what's going on between f and f prime. Then he became negative, hit that point of inflection, which became a minimum in this case for f prime, and that was when it's most negative. Then it became positive for a while, again, hit a maximum this time as opposed to a minimum, and that is reflective of this high point on the f prime. And then finally, after he starts going back down to zero, because that's where that maximum is up there, and then the slope becomes more and more negative forever. Okay, so tonight there are 9 graphs. I just want you to try your best, try to sketch them. We'll see how it works out. I got nothing else to say to you today, so take care.